So previously what I spoke on, and you can go back to other videos if you want to, is I spoke about the 12 fundamental particles. I talked about 3 of their conserved quantities: charge, baryon number, and lepton number. There's other things that are conserved as well, which I'll get into in future videos, but right now we start with those 3. Now, also a part of this standard model is 4 fundamental forces, 4 fundamental interactions, 4 forces of nature. And I'm going to discuss those today, and I'm going to discuss their relative strength, their range, and how they are mediated, what carries them. So, 4 fundamental forces that we have. We have gravitation. We have the weak nuclear force, the weak interaction. We have the electromagnetic interaction. And we have the strong interaction, the strong nuclear force. And what I want to talk about today is I want to talk about their relative strength. I want to talk about their range. And I want to talk about how they are transferred, how they are mediated across space. So let's start off with gravitation here. Gravitation has a relative strength of 1. Okay, it has a relative strength of 1. So we can use this as kind of a starting point to then compare the others. The weak nuclear force, the weak interaction, which is responsible for weak nuclear decay, protons turning into neutrons, neutrons decaying into protons, a process I will talk about more in other videos, is a lot stronger than the gravitational interaction, 10 to the 33. The electromagnetic interaction, stronger again, 10 to the 36. Now, in previous videos, from my thinking and trying to get you internalize ideas, I was establishing anchor points, things that you probably already know quite a lot about, things that you can imagine quite readily, and trying to use those to establish and make connection to new knowledge. In the previous videos, we're using like, hey, I know what an electron is, so maybe I can use that idea to think in my head what other leptons are kind of like. I know what a proton is, so I can use that to derive the properties of the quarks that make it up. These were anchor points to help us move forward. Electromagnetism, the electromagnetic interaction, is going to be something we use to go forward, because hopefully we know quite a lot about the electromagnetic interaction. Okay, we've established it's 10 to the 36 in relative strength. Okay, we should know already it has an infinite range, much like the gravitational interaction. And we have an idea of the types of things it does. The electromagnetism is a force that acts between electrically charged particles, right? We know it can combine with electric and magnetic forces acting between charged particles moving relative to each other. We know it is responsible for, many things that we're seeing on a day-to-day basis: electrostatic friction, rainbows, lightning. We can start thinking about appliances running on electrical current. We can talk about televisions, lasers, modern computers, right? We can talk loads and loads of these things about how we're seeing electrostatic phenomena, something far stronger than gravitation, but also on infinite range, very, very frequently. And we can also think about what carries electromagnetism. What is the force carrier that transfers electromagnetism? Well, that would be the photon. That's one way of modeling it, the idea of photon. So we have photons, quanta, packets of energy, carrying over an infinite range this really, really strong electromagnetic force. I'm going to be referring to that as a gauge boson. I'm referring to that as a boson. Okay, photon is a boson that's carrying the weak interaction. Not the weak interaction, the electromagnetic interaction. So this right here, this is going to be an anchor point to talk about the others. The strong nuclear force. Okay, well, the strong interaction, what's this about? This is an interaction which we find in nuclei, which is very strong, 10 to the 38. However, on a very small range. I'm not going to give you relative range. I'm going to give you this in meters, just like I gave these in infinite meters. Okay? The strong interaction is what is responsible for overcoming the electrostatic forces of repulsion between protons and the nuclei and holding them together. So you need something 10 to the 38. You need something very strong there to hold that together. Now, what's carrying that? What is the boson which is carrying this strong interaction? Well, something very like a photon. Something very like a photon. This thing is called a gluon. So what we have is inside the nuclei, we have something very similar to a photon called a gluon. But this is carrying a force that is much stronger on a shorter range to hold those nuclei together. So that's our anchor point, something kind of like a photon. So let's use that anchor point to talk about the other ones. All right, let's use that anchor point to talk about the other ones. So we can now talk about the weak interaction. Dive into a little bit of, electroweak theory, being the theory that, discusses all our weak interactions. Well, that again, not a large range. 10 to the minus 18. And as I started to talk about before, is responsible for weak decay. Protons decaying into neutrons, neutrons decaying into protons. So that interaction is being carried by, it's actually being carried by various different mediators. A series of W bosons and Z bosons is what we call them. So we have something kind of similar to photons, kind of similar to light, traveling around, right? Traveling around at a much shorter range, interacting with nuclei and decaying them. Weak nuclear decay. Protons, neutrons, protons, other examples too. Now let's dive into gravitation. These things here, we're quite, in the search for the theory of everything, the long-running equations that can predict and talk about all the physics. Quantum chromodynamics, covered by this, which includes a strong nuclear force. We've got some ideas about this. Color confinement. It's another color's another quantity that we can talk about with fundamental particles, which I haven't talked to you in any of the previously recorded videos yet. But those ideas we kind of got some ideas of. Quantum electrodynamics. Yeah, okay, we can talk about this. Electroweak theory. Great. Big gap in the theory of everything is gravitation, general relativity. Okay? On a fundamental day-to-day level, I drop the pen. Okay, cool, we see how gravitation operates. But why gravitation? What is carrying gravitation? This is all hypothetical. We were able to detect, we've been able to formalize gluons, photons, W and Z bosons. The carrying boson of the gravitational interaction is hypothetical. It is hypothetical. And that is the hypothetical graviton. Now, this isn't just wild fringe science. Most working physicists, modern physicists, it's pretty accepted the graviton of being an idea. This isn't a wild leap, but we've not been able to detect that yet. And that's one of the reasons why general relativity is this big gap in this theory of everything, which will be the composite of all these different current theories we're working with. So, the thing to hold on here, the thing I want you to try and get in your head, there are 4 fundamental interactions, okay? Relative strengths, ranges, and they all are carried by a mediator, by a gauge boson, by a force carrier. We know about the photon, and we know that carries the electromagnetic. So I don't think it's so much of a leap to say, hey, the strong interaction, that's carried by something called a gluon, kind of similar. Hey, weak nuclear decay, that is the result of the weak interaction. That's carried by W and Z bosons. Hey, gravitation, that's carried by gravitons. Okay? I can get a little bit more into each of these interactions and what they're doing in sort of some future videos, but it's all about chunking this and not going too fast, really. Internalizing things one by one, using anchors. to link to new ideas so they don't seem so alien. Because this is abstract, that is true.